Hello and welcome everyone to this session of Quantopian Book Conversation. We are very happy and honored to have Alejandro Rodriguez Domínguez with us. He is the head of Quant Research and Analysis for Miralta Finance Bank SA in Madrid. He's also the quant advisor at Inspiration Q, focusing on quantum-inspired algorithms to enhance systematic investment strategies. And lately, we have heard a lot about quantum algorithms for optimization, portfolio optimization problems, and other things where the speed ups matter a lot. And he is also a PhD researcher at the University of Reading, Department of Computer Science, working towards his PhD. And so, what we want to talk about today, mostly, but not exclusively, is his draft that we pointed out in the announcement on Quantopian. On the page, you will see the link to the draft of the book, which was on archive under QFin PM, is the Causal Portfolio Optimization Principles and Sensitivity-Based Solutions. And he also recently published, I just want to add this for completeness and a good reference for those who are interested, and we will get back to this guidance for people who are interested and want to start working on these topics. There was a paper by Alejandro called Causal PDE Control Models, a structural framework for dynamic portfolio optimization that I very much like. So that will be another topic for conversation. But welcome, Alejandro. Thank you very much for being here at this late hour in Madrid. Now,
Thank you very much for inviting me. It's a pleasure to
absolutely.
be here.
Yeah, absolutely. Pleasure is ours. If you can tell us a little bit about your interest in this area of this the causal portfolio optimization research at
Okay.
large, and also your own personal interest in that, how it relates to your work, and we go from there. We start with there and go from
My interest started since basically I was working at Miralta. We had some business that we run on portfolios for clients that are managed in a systematic approach. And I decided to basically do some work that connected what I had been studying in engineering since I was 18
there.
and what I thought that could work in finance, right? And one of the things that came to my mind first when I was thinking about this framework was automated vehicles, right? Like, for example, automated planes, in which you have a control problem and your joystick basically is autonomous, but it works based on the sensitivities that are captured for different sensors in the plane. So whenever you have information about the wind, the temperature, the altitude, all these are captured by sensors in the plane. And the sensitivities to these environmental actions is what basically makes you to the optimal trajectory for the plane, obviously, and also how you control the joystick to have a stable path over that trajectory. And that was basically the first idea. And then I decided to model assets and portfolios with PDs. I knew as well there was a second big thought that came as well to the project. That was the fact that some people were using neural networks for pricing and hedging derivatives. This was very successful since 2017. For example, in Danske Bank, the risk team there won a prize because of their framework, and it was based basically on the capacity of neural networks to approximate PD solutions and their derivatives. So it was clear to me that although you don't know the PDs of assets and portfolios, you can get the sensitivities or the partial derivatives with data. Okay, and for example, the one candidate model for that could be neural networks. Then when you start modeling the problem of a portfolio, you realize that, and this is something that went during the process, you realize that you don't really need to forecast assets, or you don't really need to focus on what are the optimal drivers of assets, because the problem of portfolio optimization is based on diversification, right? And you are really interested on the dynamics of diversification.
Mhm.
And when you are dealing with diversification, it turns out that there's a set of drivers that are optimal in terms of what would be the optimal selection for understanding the dynamics of the diversification. And it turns out that basically are the common causal drivers or we don't need to go to the causal part, but at least you need to have the drivers that are optimal for the portfolio should be the optimal drivers for the constituents that are mostly repeatedly selected among the constituents of the portfolio. So, for example, if you have a candidate universe of drivers of 1,000, let's say you are looking for 20 or 15 drivers, obviously each constituent will have its optimal set of drivers, okay? Why? Because it will be the optimal predictors for these constituents. Okay, if there is a common selection among the optimal drivers for the constituents such that they are most repeated among all the constituents, then you start having a common set of drivers for the portfolio. It turns out to be that the most you get into that property, the geometric space that is formed by these drivers meets a certain properties that allows you to have this causal diversification, so to speak. And I say that I didn't include the causal point because that came just as obligatory for the framework, so to speak. So it's not like we're going to try to basically fit causality into this framework. It's the other way around. We understood that in order to have this space to be able to give us the information about the dynamics of diversification, they not only have to be common, the drivers, in the sense that the most repeatedly selected among the optimal drivers for the constituents, but they also have to be causal. And we published a paper in 2022. Well, the paper was in 2022. It was published in the following year, in which we basically present this principle, which is basically the commonality principle, and is the only way you basically can have this space of drivers that allows you basically to preserve the causal properties in time, right? And we present the proofs in the paper, but they are quite straightforward. The conclusions are quite straightforward and very easy to explain, right? So, I can give you here the conclusion. So, the key point is first you need to define what is, let's say, optimal diversification. Okay, when you're using factor, because we all know that idiosyncratic diversification is what you obtain when you are using Markovitch. Okay, but that's the unconditional case, so to speak. So that means that when you only have information about prices, you can get the optimal amount of idiosyncratic diversification by adding more assets. But it turns out that when you start using factors, you cannot maintain the same level of idiosyncratic diversification while adding systematic diversification. Why? Because some things compensate with each other. So you end up having, when you are using factors, you are basically projecting your portfolios into the span formed by these factors. Right. If these factors are not common and causal, you're basically going to have a trade-off between idiosyncratic and systematic diversification. So in order to have the maximum amount of diversification, you want to keep the level of diversification that you obtain with the Markovitch case, the idiosyncratic diversification optimized, but also adding systematic diversification. And for that, you need to preserve the proportions of the angles that the returns have on the unconditional case when you move to the conditional case. That means you don't really need to preserve the same angle between two returns in that space, because obviously when you are conditioning, all the space changes, but at least the proportion, they need to be proportional. So in the unconditional space, you will have returns that will have angles in between, and the cosines will be the correlations. When you project into a space in which is made up of factors, the angles will change, obviously, but they will change proportional. So all will change such that the proportions are respected. And in that case, you will have a conformal map, so to speak. It's what is called. And in order to have this conformal map, you obviously need the factors to be common, because otherwise this conformal map is impossible. And this is what we show in the paper. And they also need to be causal, because if the map from the unconditional to the conditional case is only a function of time alone, okay, then it's not a function of which driver do I select as optimal. So I cannot switch the
Yeah.
driver.
Yeah.
It will be only a function of the drivers that I have selected and how they evolve over time. So in that case, you will not have the case, obviously, in which you don't meet the properties of the space of having the same canonical set of dimensions, but you won't have the case in which you will need to change one driver for another that is not in the sample, because it will only be a function of time alone. And if it's a function of time alone, all the angles change as a function of time, but the proportions are preserved, because it's a constant, okay? So in order to have this property, that's why they need to be causal, to be a function of time, and need to be common, so that the canonical basis is preserved. And this kind of to show people something that is really simple in a sense, that they need to be common, but it's quite important, okay? Because it's something that allows you to simplify the causal identification algorithms. So if you want, for example, to go into a universe of drivers, you now can build the causal graph, so to speak, that you're going to look at. It's going to be one in which the drivers are going to be the parents nodes, and they're going to be connected all to the same set of constituents. So then you, with this graph in mind, then you can go systematically or combinatorially to a set of a lot of drivers and get the ones that maximize the probability of having this causal graph occurring in your data set, so to speak. This is also, it turns out as well, that when we were thinking on all this, we were highly influenced by, for example, the common cause principle by Reichenbach, okay, in which he basically says that a correlation between two things must exist either because one causes the other, or vice versa, or because there is a third cause that is causing both, right? And there are a set of independent conditions that the variables need to be met in order to have a common cause to exist. So this previous causal graph that I was mentioning, in which you have the parents all connected to, in the end is Reichenbach combinatorially applied across all the spectrum of combinations of drivers and assets. And once you have this common causal system, which would be the network of parents connected to the assets, then you look into a sample, which will be a big universe of, for example, the whole Bloomberg terminal, 25,000 time series. You will look at which ones are maximizing the likelihood of having your causal graph, in the case you use maximum likelihood estimations, or you can use causal Bayesian networks and come up with the best, that the ones that best fit. Or you can even use correlation as a proxy, because correlation does not imply causality, but causality implies correlation. That's right. If you are maximizing the chances of having causality, hence correlation must be helpful around searching in that optimal space of solutions, you see. So you can prune the search space of optimal solutions by using correlation, obviously. So the combinatorial space, the combinatorial problem is reduced in computational cost. But then we say, okay, so now that we have the optimal drivers, what do we do with them, okay? You would expect to simplify the old framework as if you were thinking of the portfolio like a derivative, and you were thinking of Black-Scholes, like when they were thinking of option pricing and the risk neutral measure, and all assets having the risk-free rate conditional on being on that risk neutral measure. Okay, so if you are in this common causal driver span, it turns out, and not by any magic, but by very simple maths, that if the assets are projected into the space of common causal drivers, they must be independent. You see, assets must be independent in that space. So it turns out that conditional on that space, the portfolio must be conditionally risk neutral, so to speak. And if you think of the homology with Black-Scholes, it would be like if you would have a conditional risk neutral measure, and what is important is the drift of the common causal space, because conditional on knowing the information of the drivers and their movement on time, then you have your portfolio is diversified because the assets are independent. So, and that's basically the key idea. And then you can start building up on that. For example, we have a paper in which we develop, like in a Black-Scholes way, what would be the conditional PD there is the conditional risk neutral PDE for portfolios based on this idea, assuming that the portfolios are independent condition on this conditional risk neutral measure. Also, you can have then more extensions, like for example, in terms of how you get to the optimal weights, right? That would be the next question, because now you have the drivers, you have the space. So there are two possible ways. Either you optimize in the vector space formed by the drivers by using, for example, covariance matrices or distance matrices of the factors of the returns of the constituents conditional on the factors, the standard factor-based optimization approaches, in which they basically use the statistical measures of the conditional probability of knowing the returns conditional on the factors. Or what you can do is also look at tangent space on this manifold and kind of serve the manifold with the tangent space. And I will explain what I mean by that. I actually have a figure I can show here. Basically is where you see the combinatorial optimization search, in which you are basically just applying the independence conditions of Reichenbach. You apply it simultaneously to all the different pairs of assets and for a given set, optimal candidate set of drivers. And basically by doing this minimization, you are basically trying to maximize the probability of these conditions being met with this causal graph in a set. Let's focus on this figure on the left. So you have this factor space or common causal driver space, but the thing is, this thing is moving in time, okay? So your tangent space, your solution will be moving in time as well. The solutions, the optimal weights or solution on that space, no matter if you do it in the tangent format or if you do it, for example, in this case. So let's say the span of drivers is this plane, and you're basically will be looking at the projection of the portfolio in that plane, and conditional on being in the intersection with the simplex, which is the properties of the weights, you will get your optimal portfolio. This is basically the standard Markovich or extensions way of having an optimal solution. But you can also look at the tangent plane, right? You look at the sensitivities. And when I'm saying sensitivities, I'm not saying there is some part of the literature that speaks about sensitivities with respect to risk metrics. And they do portfolio optimization by using, for example, sensitivities. They use sensitivities with respect to value at risk or conditional value at risk, and they do an optimization problem by kind of using the information of how sensible are the different weights with respect to these metrics. I'm not using that thing here at all. When I'm talking about sensitivity, I mean the derivative of the constituent for all constituents in the portfolio with respect to the set of common drivers. For me are sensitivities, because as I mentioned, our premise was that we were using partial differential equations that we don't really know how they look, but we can approximate the partial derivatives with any model. I mean, if you want to use the most simple model, you can use the betas of multivariate regression. But if you want to get the things better, you will use nonlinear models or neural networks. The point is, this partial derivative will give you, or the expected value of this, because you are using data to approximate it, will give you this sensitivity. And these sensitivities can be used as coordinates to basically embed the constituents in this sensitivity space. Once you are in that space, okay, is where you are here, then you can do two things. Either the manifold can move, because the drivers change, they could change in terms of the candidates, or they change in terms of, obviously, they have their own stochastic differential equation and their own time evolution. So the tangent space can change as well. So it turns out that what we did is we came up with an idea. Is you can either assume that the common causal manifold is fixed, and you can surface that manifold with the tangent space, or you can either have the manifold move in time but having fixed the tangent space.
Right. Okay.
Okay. If you do that on each iteration, you end up having a causal system. And it turns out that it meets the definition of a causal system in any field, because if you go to the definition in engineering or in telecommunications or physics, those are the causal time systems. Okay, there are causal time systems. And the key point is, okay, so let's assume we have 30 timestamps. We can, this, you're always going to have this property of causal time systems in the sense that either you can move one time with the manifold fixed, or you can leave the tangent space fixed and move the manifold one time. Obviously, you're going to have a property in which you're able to estimate the best path among these two possible options. Okay, if you iteratively do this, you will end up having maybe 30 timestamps for common causal manifold, and you will have possible trajectories, which are, they have two possible paths. One is the relative path conditioning on having the manifold fixed, and the other one in time, and the other one is the absolute path, which is the one that takes into account how I move in the manifold and how the manifold moves. Okay, and you end up having a term structure of sensitivities, so to speak, because, and this is for example, one of the ways we show in the documents that we have in archive, okay, which basically assumes that you can have a lag in your process, okay, and get the sensitivity for different lags. So that means you have a PDE that has the relationship between the returns and the drivers by lagging only one in time, then two in time, three in time, up to n in time. So the sensitivities are going to be based on processes that are lagged, okay?
Yes.
And this is going to give you the dimension of time when the manifold moves. On the other hand, so this sensitivity is going to have information of how the manifold, let's say, is moving. And on the other hand, you have obviously that conditional on being in one time, you have a set of optimal candidates for your parameters. And that's also giving you, paths in the same manifold for a given set of time lag. So you end up having a term structure of sensitivities. And because you are having a term structure of sensitivities, and it turns out, and we proved this with all the drivers we had, all the constituents that you can think of that we had, turns out that the sensitivity, when you approximate it with data, and you look at the distribution of these sensitivities, the sensitivities in the end, when you have data, 150 timestamps, for example, when you use neural networks to approximate the sensitivity, you end up having 150 values of the sensitivity, okay? The end, the sensitivity is a function. And because you're approximating with data, it's a discrete function. So it turns out that for any possible combination of asset class, or if we mix different asset class in the portfolio, or if we increase or decrease the number of constituents, we change the type of driver, for example, the whole set of candidates that you can take in terms of macroeconomic data, pricing data from derivatives, FX data, index data. So anything, it turns out that they all behave like a Cauchy distribution, okay? I mean, it's like a universal law. The sensitivities behave like a Cauchy distribution, which it turns out that is very similar to interest rates and short rate models, and how short rate models distributions are. So we thought of this, and obviously it was a perfect fit to use short rate models like basic JEG or as Hull and White as stochastic differential equations to model this sensitivity. So one of the things we do, for example, is, and now I can speak about the optimization methods. As I said, we can do the usual optimization, or we can come up, we have these neural networks in which we have the assets and the same set of common causal drivers. We get the sensitivity, we project the assets in the sensitivity space. Okay, now the trader is going to say, I don't understand risk in this space. Tell me the risk in terms of volatility, or in terms of valid risk, or conditional valid risk. There's no issue. You just do a map from this space to the space in which you have the risk measure of interest. In our case, for example, in the first paper we published, the map was done by a hierarchical clustering. And let me explain why. So imagine we have assets projected in this space. This space basically has causal information, of course. It has information about the trajectory of these assets. The risk is not defined in terms of volatility, but the hierarchies that you can make if you compute a distance matrix on this space. So here we have assets that are projected in this sensitivity space. We can come up with an Euclidean distance of these assets in this space. This is going to give us information of how far or how close these assets are in this sensitivity space. Okay. If you compute a hierarchical clustering on this distance matrix in this distance matrix of the sensitivities coordinates, the hierarchies are going to preserve the information of this causal space and these dynamics of risk in this causal space. And then what you do is, once you have all the clusters made up of in your hierarchical clustering that are respecting these hierarchies, you compute the variance covariance matrix of these clusters, and you weight your weights, like risk parity, so to speak. You weight your weights based on the hierarchies of and the variance covariance, or the variance and the covariance values of these clusters made up in this hierarchy, but that is made up of hierarchies from the sensitivity space. So you're kind of applying what is called hierarchical risk parity or hierarchical equal risk contributions. These methods that basically apply a hierarchical clustering in the correlation matrix, and they try to come up with how they are clustered in the correlation matrix, and then they weight the assets based on these hierarchies.
Yep.
Okay, we apply the same, but applying the hierarchical rule is made up of the hierarchies they make in the sensitivity space. So this is, for example, what we applied in the first paper, but what is going to be in the book, and obviously we did extensions later in that's why we published also another paper that is the PD causal control. Here we include all the possible optimization schemes, because as I mentioned, you can either apply traditional methods like Markovich, but you can apply entropy pooling, you can apply Black-Litterman, you can apply any method that is applied in factor investing, you can apply it into the space of common causal drivers. In terms of the sensitivity space, you can use, for example, hierarchical, as we did, or you can use optimal transport map, you can use copulas. There are many different techniques that basically allows you to map from the sensitivity space of risk to your risk measure of interest. Also, one of the things that we did in the last paper is we did not apply short rate models to basically thinking of what you do, for example, in rates, in which you have a term structure of rates, you have the short rate models to basically have a path in between all these term structure of rates. You could do that, but we have another way of applying this, is in which basically, if this is the common causal manifold, we basically apply an optimal control problem with future states of the manifold, so that the independence property that I explained before that is happening in that manifold is met, or you maximize the chances of having this property met in the future. And it turns out that it can also be measured by being a conditional martingale. So you can also have a control problem in which you basically control the manifold to be a martingale in future states, the portfolio conditioning on future states of the manifold. And this is what we did in the PD control last paper. We applied the Jacobi-Bellman equation, and the backward stochastic differential equation solver to control for the fact that, okay, given the fact that I have a set of common causal drivers that makes my manifold, what would be my optimal solution if I don't deviate from these conditions of being a martingale in this subspace or manifold, and meeting the common causal risk neutral property, because they are independent in that space. And all these things are going to be in the book in a combination of things that we find interesting in between these methods, so to speak.
So this, I want to go a little bit back to where you started, just ask if I understood it correctly. So this whole idea of causality really comes in because you are asking in the theorem for the necessary sufficient conditions for the existence of that conformal mapping.
Correct. You need causality because in order to have optimal idiosyncratic plus systematic diversification, you must have this conformal map.
Uh-huh.
Hence, you
Yeah.
need the drivers to be common causal. In any other case, it turns out that the space will be a function of time plus which driver is optimal for that specific point in time.
That's okay.
If the drivers are causal and common, you don't care in time t and time t plus one, which is the other optimal set of common causal drivers. Because the fact that they are common causal means that they're persistent,
Yes.
and means that in t plus one, they're going to be the same. So it's the only case in which, and therefore causality arises as a necessity.
As a necessity.
In that case. But it turns out that it goes as a necessity in other areas as well, because when you're using, for example, PDEs, okay, there must really have these sensitivities. There must be some form of causality between these drivers and the returns, okay, the returns dynamics. There must be some form of causality between what the drivers are doing and the return dynamics in order to this PDE to work, okay? Otherwise, it's not the true PDE of the system, because you will have, especially if it's a function of time, because of the same properties, then you will have the variables changing in time as candidates. Your equation will change. So if you have a PDE of, for example, the Navier-Stokes equation, you don't change the variables as a function of time. You have the same set of variables in your equation. What they change is the values as a function of time. So hence you also need causality because of the PDE, your approach of using PDEs. It's true that we don't identify which are the PDEs, but we don't care because we look into the projective space, and for that we want the partial derivatives. Right. Having said that, if you have extra information of the asset or of the portfolio, because they have more momentum, or because you know that they are more, they have more tendency to jump than others, you can obviously change the PDEs. And this is one of the good things that the neural networks have. They have a lot of tools for automatic adjoint differentiation, in which you basically can modify your PDEs. And when you do by backpropagation and apply automatic differentiation, your sensitivities are going to be a function also of the structure you choose. Also, you have physics informed neural networks, in which you basically, it's not like, for example, doing automatic adjoint differentiation, but you add into the loss not only the approximation error of the neural network, you also add physical laws that are impacting in the weights of your network, and obviously the relationship between the output and the input, and hence the sensitivities. So the sensitivities can be based as well on other physical laws that in finance, those physical laws are, should I care more about the momentum the assets have? Should I put some penalties on the dynamics of these processes? So it's a very extensive framework in the sense of it uses very important tools in the sense of that allows you to a lot of flexibility, and the amount of opportunities when you combine them it gives for a lot of content.
Well, which is a good direction to go, given all the new things that are available and the speed efficiency with which one can do things now. I mean, if we didn't have neural nets, you wouldn't be able to change even one of those things to see what happens next, or change multiple times to see what happens. So sensitivities play a central role, and they are computed using these neural nets. But sensitivities themselves can be a function of the structure, as you were saying, as because each sense, the way I understood it, you take the partial derivatives of Ri with respect to dj, and that will be the sensitivity of
the constituent with respect to the set of same common drivers.
with the
So,
certain
for example, this is a portfolio of stocks from 1 to n.
Yeah.
So, but you put as input the same set of common causal drivers that you got from your solution.
That's right.
In here.
Yeah.
So by automatic differentiation, okay, in this case, then it depends on the structure you are using for your network, okay? Because depending on if you use a feed-forward network, then the solution is straight away, okay? It's very similar to backpropagation algorithm. and you get the derivative of the output given the input, and that would be the sensitivity, because you have, for the same output, which is one asset, you have the 10 inputs or the 10 sensitivities for that output. And then you repeat the same process for the other stocks in your portfolio. Also, one of the reasons why we said that they must be common is because we need the same set of inputs
For all
into
of
the
them.
neural network
That's
in
right.
order to have the whole thing to work. Otherwise, you don't have the geometric properties to project into the tangent space. But the thing is that you can, instead of using feed-forward networks, you can use recurrent neural networks.
Yep.
Then, when you use backpropagation and you compute the sensitivities, or the sensitivity of the output with respect to the input, which will be an approximation of the partial derivative, it will have this recurrent component included as part of the sensitivity. Okay, and here we're only adding a recurrence.
Yeah.
But imagine you make more complicated the network. You
Sure.
will make more complicated the way you compute the sensitivity. But there are tools available. TensorFlow was very good at this.
Yes.
It allows you basically to compute sensitivities quick, and you were able to basically connect the different networks one on the other to come up with, which basically is the skills that you use in the sell side when you are pricing derivatives with neural networks.
Of course.
Okay,
That's
because
what people use. Yes.
they if you want to, for example, compute an option with Black-Scholes using neural networks, you don't use a feed-forward network. You need basically to replicate, so to speak, the path in the derivation that the Black-Scholes is giving you when it gets the solution. You need to replicate that with neural networks and then compute the which is called the adjoint. So you add and you join different networks, and then you by propagation get the derivatives, which are the Greeks in the case of the Black-Scholes, or in this case the sensitivities, which are giving you the space for optimal solution of your portfolio.
And one thing before I open it for everybody else to see what questions they might have, you did mention control theory multiple times, but how does that work here in terms of, so in control theory you have of course you have a manifold in most general case, in the geometric at least version, and then you have a starting state and you have control inputs, and then the system is obeying the dynamics of its behavior, however it is given. Let's say this partial differential equations describing its behavior on the trajectory going to a particular target point where you want to get. And then you design this control input in a way that in a given particular amount of time or bounded by some time, it gets you from the initial condition to that desired final state. So what are those things here? Like if I am, let's say in the more practical sense, if I am a customer, either you or I, and we sat together, we have decided what these x's should be. Okay, we decided those. And then we have these A1, AN, and all that. And then what are the things we are controlling now to get to a particular final state?
So you're basically controlling the fact that as soon as your solution lies in the manifold, okay, in the tangent space, you're fine. The problem is that I mentioned the tangent space can change either because the manifold changes,
yes,
or because you move on the manifold.
Yeah.
So the control problem is finding the weights, okay, because that's the problem you want to get.
Okay.
You want to find the weights. You want to find the optimal weights of your portfolio. That's your control. You want to find the weights of the portfolio such that when you have these weights multiplied by the returns, hence you have the return of your portfolio, the trajectory of the portfolio lies on the tangent space of this manifold, conditional on the fact that this manifold is the optimal common causal manifold.
Right.
You see, and this is one of the things we do in the last paper, because in the first paper, or in the archived version of the manuscript, in which we showed the term structure of sensitivities and how you can interpolate with the stochastic differential equations, it's not a control problem, because it's more a simulation-based problem.
That's right.
But in the new paper, it is a control problem, because you are basically restricting yourself to trajectories of the portfolio by controlling with the weights, such that those trajectories lie on the tangent space of the common causal manifold. And if it change the common causal manifold because the drivers change, or because time change, the trajectory must change. You see?
Yep. Which makes sense. All of that makes sense. Yeah. Okay. Thank you. Yeah, I understand. now how that control problem is defined and used.
Just to let you know that the first paper that we published in 2022, it's this one. So I think it went live in 2023.
Mm.
This paper has a code on the
Ah,
journal. So and it basically has a Docker file in which
okay.
you have access to a set of 1,000 drivers and couple of portfolios, and you can run multiple simulations of experiments to see how the method compares with other methods in the
Uh-huh.
literature.
Oh, you do
And
the okay, okay.
you can select all the hyperparameters. You actually have access to the code, so to speak.
Perfect.
So
Perfect.
if you can modify the code, you can get the code, you can do
Yeah, yeah.
the next papers. The code will be probably in the book. We will share the code in the
Okay.
with the book.
Any ideas on when the book is, do you think will be completed roughly? Oh,
Next
next
year,
year. Okay.
I am. Yeah, I have a very kind of limited schedule in the sense that while doing the PhD publishing and then working on the book, but I have the contact with the and the relationship with the publisher and we have some deadlines that we need to meet, and I would expect 2026 by the second half
Yeah, makes
to have
sense.
the book.
Oh, that would be very nice. Very, very nice. So, two questions at least remaining. One is, what are the challenges that you see coming in with this approach? Or, in other words, I should phrase it perhaps better. What was the most challenging part of the work? And what, if somebody or you yourself wanted to extend this work, what are the challenges that you foresee will be on their way? I'm probably mathematical
I
challenges.
mean, the challenges that I faced was trying to adapt the framework to the standard language that
Ah,
is used in the literature. You see, because you have finance literature that is not very, especially the portfolio management literature is not very rich in stochastic calculus and control theory.
no.
You have the control theory and artificial intelligence literature that are very rich in, but not rich enough in finance. So trying to unify all that and be able to publish with the peer review is obviously challenges, because even if you know that the models will work and you have the code, you need to basically come up with an explanation that meets the four aspects of the literature. And so that was challenging. And the second point, I would say that you will get better performance if you have colleagues that helps you in some process of this of the implementation of these models. What I mean by this, this is not something that you basically get into your house and you connect it to a cloud and you input it into a broker, because drivers can be anything, even textual image, satellite image,
Yeah,
it can
yeah.
be any form of time series. So if you have a set of qualified people that makes you the search space reduced, that
Mm.
will help a lot. And it helped me a lot the fact that I have portfolio managers that are with a lot of experience in Miralta. Another thing I would say is you need to basically have people that understand how to transform from PDEs and PDE modeling to neural networks and approximate these neural networks,
Uh-huh.
which you have strong people in the sell side, hence the deep hedging culture that is growing up a lot.
Mm.
But still, in many portfolio management teams,
Mhm.
you will not have this. You will not have this. This is very sophisticated for them. You will have a lot of different things that are the same or more sophisticated, but not related to this culture that comes from the sell side of the PDE and risk neutral way, even if conditional risk neutral way of thinking is it hasn't been suited in the buy side that often, and now it's growing, but we need more time to grow. You see.
Yes, definitely. And incidentally, based on what you're saying, going back to what you said about PDs and neural nets, even up until couple of years ago, it wasn't a big thing. There weren't that many people compared to everything else that was using neural nets and with all the, excitement around it. this idea of applying it to partial differential equations and other things, these are relatively recent things that came into play. And as you
And
say,
one of the first people that made this famous were from finance. You
yeah,
know, this team at Danske Bank that has produced some of the most well-known quants in the world. Antoine Savin, for example, is one that is working now at HRT in the States, one of the biggest hedge funds in the world. He used to be in that team. He actually had papers called differential machine learning. They were applying this for pricing derivatives. Now he is in a hedge fund applying what he knows about PDEs and all this stuff into the buy side. But yeah, I mean it's actually new, and probably if we wouldn't have this, we will be doing it with multivariate regression. We will using betas, which you can do in this framework, because as soon as you have the optimal set of common causal drivers with any method that you may want, you can still use betas as your sensitivities
that's right.
to project the assets there.
Yeah,
So
yeah.
it's true that from all the experiments that we have done, and it's not a surprise because of what you say before, neural networks, physical neural networks, and the control implementation, the control theory implementation works better than the others. But it turns out that, for example, when we do in the paper a comparison between the baseline model, which are the rest of models in the literature, and we apply the control solution and the common causal identification solution, they improved a lot. So it means that you are not only improving by something that you don't know, you know that these models can improve baseline models too, which
Wow,
is
that's quite impressive. That's actually very impressive. That's right.
yeah, thanks.
Well, coming to my last question to you is, let's talk now about a little, if somebody wanted to get started with this research, and or if we wanted to create some educational material. Remember, we had talked, you and I, about the possibilities of maybe teaching something on Quantopian that had to do with the causal portfolio optimization. At that time, I didn't know exactly where this or how this causality got into the picture, but now, thanks to you, I have a much better idea. But if we were to put an educational pathway for people who wish to get involved in research like this, what would your recommendations be?
I mean, my first recommendation, I think this engloves a lot of more profound ideas about what is going on now in the literature. You have some hype in causality and all that. I mean, imagine you want to do a course of portfolio optimization, and if you didn't have to basically focus on the historical way they have been teaching this, you will start by geometry and trying to make people understand how geometrically you are solving the problem. Because in the end, portfolio optimization is a problem of hedging, and hedging is a problem of projection. And that's it. I mean, then is where you stop, because Markovitch can be the best model available if you have the best projective space available, which means the best set of factors in which you project. So a factor model with Markovitch can beat any single model in the world if they have the best optimal set of candidates factors. Meaning that, I mean, and that's more so for students knowing the geometry behind the concepts of risk, return, diversification, the fact that you are projecting into a space and then coming up with the solution that basically allows you to hedge simultaneously all the risks. The fact then going in a second stage from Euclidean to non-Euclidean geometry is telling them that you can solve your risk problem in a different geometry than the one that people live and then project back. This gives people a set of tools that are framework dependent. They are not model dependent.
Correct.
And then when you have these recipes, then you can show them a list of 20,000 models and they will be able to apply them into the framework understanding, which is something that is not done in the literature by many, because they basically, for example, try to say, let's apply Judea-Pearl framework to factor investing, for example. I mean, does it really make sense that? Because in the end, Judea-Pearl is a set of rules that were invented by computer scientists, that they work in a highly controlled environment, and normally they work for predictive capabilities, because a robot not was invented to basically hedge its risk by projecting, their paths into a projective space. It's not like that. So So basically, you're trying to get something, trying to force the science to work, whereas you haven't understand the problem you're trying to solve. So the first thing is try to understand what portfolio
What is
optimization
it?
is about,
Yeah, huh? Yeah,
and
yeah.
then you will be able to englobe it with the set of methods available.
Do you know of any literature or foundational literature that pursues this kind of geometric approach to portfolio optimization?
No, no, that's why we are doing the book,
That's
because
yeah, yeah,
it's you have it in multiple science and in multiple papers. You don't.
scattered all
I
over the
mean, you have differential geometry, but it's not linked at all to the to risk or the properties
right.
of risk in a portfolio. Or you have some applications of risk with information geometry and PDs, but there is not a unifying framework. I mean, the
Mhm.
unifying framework I would say is the set of papers that we're publishing, that hopefully they will come up into a version, all of them together in the book.
Perfect. Perfect. That would be wonderful. Meanwhile, I'm going through this and I'm trying to extract and write up things that because I very much like that approach. I know maybe there are people who won't like the geometric approach, just like everything else, like there are people who are more on the algebraic side of things and more, on other but I also believe, like you do, that this geometric approach is a foundational sort of bedrock to build this thing on top. It's so rich. If you really use it properly, it can really tell you the whole story, even of the things to come in the future. Because
Yeah, and even if you're doing algebraic or whatever, you are incidentally you are using geometry. The thing is that you are not
hidden under the
um,
edge. That's right.
exactly. It's like, for example, when people do quadratic programming, they don't think that they might think they're not doing geometry. They are actually doing geometry. The only thing is they don't want to look at that spectrum. I'm happy with that, but the point is you cannot do hedging into a metric space unless you do geometry. I mean, I don't see it's complicating yourself because you don't want to do things the way they are. I mean,
Yeah,
it's highly complicated in
yeah.
that way.
Very true. Very true. Well, thank you very much, Alejandro. This was absolutely fantastic. Thank you very much for taking the time to explain all this material that you have been so successfully working on. I am really eagerly, excitedly waiting, looking forward to the book. And I'm sure
Thank you
that
very much.
I'll communicate more as I go through these, and I will have tons of questions for you. And if others who are listening to this on YouTube or some other time and you weren't here, I'm sure that Alejandro will be happy to answer questions if you read the book
Sure.
or the papers or the code or just you want to experiment, you don't want to do anything with math, but just want to play around with it, that is fine too. But this is
Yes, as a guide, I definitely suggest to go to the causal portfolio optimization principle and sensitivity solution, which was the first set of proofs and principles that we wanted to put live in archive, just for a matter of that we were sharing documents with the publishers, and we
yeah,
wanted to put it live in archive. So I would start with this document and then go to the paper of the
yeah,
last one that
the
that
last
we
one that you
published.
said. Yes, yes. If that was exactly the plan I was going to pursue, the draft of the book, which was on April 2025, April 9th,
Yeah,
that you put on archive, and then this causal PD control. Because I really like the control theory framework, and control theory has done a lot of geometric work. Geometric control theory is a field, as you know, on its own. And
yeah.
so once one connects properly with that side, one can carry over all that stuff to this world, which will, yeah, as you as you see yourself, takes a lot of work.
Yeah, it goes back to the plane that you want to automatically fly, right?
That's right.
Remember at the start of the conversation.
That was the start of the cut. Exactly right. Exactly right. Yeah, and these become even more complicated, as you were saying, than robotic problems, or most robotic problems, if not all of them, or aviation problems. They become really highly complicated and way too many parameters, too many things changing, too many times, and all that stuff. But that is what makes it fun too. I suppose.
Yeah, and that's one of the good things of working in finance, right? That you don't really
Yeah.
have to get everything right.
Yeah,
At least a percentage of the solution. So
that's right.
that's also beneficial.
That's right. That's right. Like here, accidents, robot may bump into a wall and nothing bad may happen too much. But if you fail a $1 million project, well, not the same thing. Not the same thing.
Yeah, but you can think the other way around. Like, for example, if a plane make a mistakes, you may die. But
Of course, if a man,
if you, for example, make a mistake on a on a threshold of your parameters, you might lose only, I don't know, 3% out of 30%, or that you have a much more freedom of failing, I would say,
failing,
on
right?
finance if you do the things right than on autonomous flying, for example.
Yeah, most of the correct. As soon as human beings are involved in your flight or in your robotics project, the table changes, but the balance changes very drastically. But if the vehicle is itself or a drone or whatnot,
Exactly.
yeah, fantastic, fantastic, wonderful. Best of
Yes.
luck to you with the book and the PhD. And
Thank you
thank
very
you
much.
so much. And good night to you, and good day or good evening to everybody else. All right.
Thank
Talk to
you.
you later.
Bye.
Bye.